So have you ever really stopped to think about what happens when the battery in an electric car finally gives up the ghost? I mean, it's not just the end of the road for the car. It's actually the beginning of this fascinating, multi-billion-dollar journey. And today, we're going to go inside the high-stakes world being built from the ground up to give these batteries a second life.
Okay, picture this. Your trusty EV. It's been with you for a decade, maybe more. But that massive, really complex battery, it's done. So what's next? Does it just become some giant toxic paperweight sitting in a landfill? Well, the answer is way more complex and honestly, a lot more interesting than that.
And look, we're not just talking about your car here. We are talking about a literal tidal wave of batteries. By the early 2030s, the industry is bracing for more than 15 million tons of EV batteries to hit their end of life every single year. That is a staggering number, and figuring out how to handle it is one of the biggest industrial challenges of our time.
Yeah, this isn't just a waste problem. Insiders are literally calling it the battery tsunami. And for the companies trying to navigate these waters, it's both this huge, immense challenge and an absolutely incredible opportunity.
So the journey of turning this hazardous waste back into a valuable resource, it doesn't start in some pristine white coat laboratory. Nope. It begins at a massive, highly engineered industrial facility, just like the ones run by a company called European Metal Recycling, or EMR. This is ground zero. And the very first stop once a car gets there is a place called the depollution bay. You know, before any of the high-tech chemistry can happen, there's a whole lot of crucial, hands-on mechanical work that has to be done. This is where they really get their hands dirty to make the whole process safe. What's really cool here is just how systematic this whole process is. First things first, they get that high-voltage battery out, which isolates the biggest fire risk right off the bat. Then, all the hazardous fluids, oil, fuel, you name it, are drained. Next, and this is so critical, they safely deploy explosive components like the airbags. You do not want one of those going off inside a giant metal shredder later on. And finally, the tires come off for their own separate recycling journey. Okay, so after all that prep work, the battery components get shredded down into this stuff called black mass. It's this fine black powder, but don't let the simple looks fool you. This stuff is basically 21st century gold dust. It's packed with that valuable cocktail of metals, lithium, cobalt, nickel, that everybody is fighting for. This is the precious raw material that's about to head to the chemical refinery. But how do you actually get those metals out of the black mass? Well, right now, the industry is at a crossroads, facing a choice between two competing technologies. It's really a battle between the old-school furnace and the new-school sieve.
And this table just lays out the difference perfectly. On one side, you've got pyrometallurgy, the furnace. It's just brute force. You melt everything at over 1400 degrees Celsius. It uses a ton of energy, kicks out a lot of CO2, and this is the most important part, it's terrible at recovering lithium. But then you have hydrometallurgy, the sieve. It uses low-temperature, water-based chemistry, it's way more efficient, has low emissions, and it can recover over 80% of that critical lithium. It's a no-brainer, right?
So, faced with this choice, MR made a huge bet. Instead of trying to reinvent the wheel themselves, they made a really strategic investment in a tech company called Renewable Metals. Why? To get access to their advanced hydrometallurgical process, their next-generation chemical sieve.
So, what's the secret sauce? What makes this particular sieve technology so special? Well, it all comes down to something they call the alkali advantage, a fundamentally different and just much, much cleaner approach to the chemistry.
Okay, so here's the dirty little secret of most hydrometallurgy. It uses really strong acids to dissolve the metals. But then, when you neutralize that acid, you create these massive amounts of a waste product called sodium sulfate. It's a huge environmental headache, and it costs a fortune to get rid of. But the renewable metals process? It uses a proprietary alkali, or basic, solution instead. And the magic trick? It produces zero sodium sulfate waste. None. This is a total game changer for the economics and the environment. And get this, the performance claims for this alkali process are just staggering. We're talking recovery rates of over 95% of critical metals, including that all-important lithium. It runs at low temperatures, which saves energy. It's flexible enough to handle different battery types, like the newer LFP chemistries. And the final product? It's high-purity, battery-grade material that's ready to go right back into the supply chain. And that brings us to the final, and maybe the most important part of this whole puzzle, closing the loop. You've successfully recovered these pure metal salts from the black mass, but how do you turn them back into actual battery parts and complete that circle? Right, so you have these bags of super pure metal salts. but they aren't a battery component yet. Someone still has to take on that final, really complex step of turning this powder into the precursor materials that a gigafactory actually needs to build new batteries. So who does that?
The solution is this brilliant distributed circular economy, and it's built on a three-way partnership. It works like this. Step 1. EMR uses its huge logistics network to collect the cars and make the black mass. Step 2. Renewable Metals uses its special alkali chemistry to refine that mass into pure salts. And then for Step 3, a chemical giant, Johnson Matthey, steps in. They take those salts and synthesize them into the advanced battery-grade materials needed to build brand new cells.
And as this quote really hammers home, this whole closed-loop system is about one thing: resource security. For car makers and battery manufacturers, having a reliable, low-carbon, domestic source of these critical minerals, that's a massive strategic advantage. It frees them from depending on volatile and, let's be honest, often ethically complicated global mining operations.
But let's be real for a second. While the tech is brilliant and the business case makes sense, this entire multi-billion-dollar industrial revolution is being pushed forward at lightning speed by one incredibly powerful force: regulation.
Just look at these mandates coming out of the European Union. By 2027, recyclers have to recover 50% of the lithium from old batteries. Just 4 years later, by 2031, that target skyrockets to 80%. Remember that old furnace technology we talked about? There is no way it can get anywhere close to those numbers. These rules make advanced hydrometallurgy not just a nice-to-have advantage, but an absolute necessity for survival in this business.
So the technology is here, the partnerships are forming, the regulations are forcing everyone's hand, all the pieces are falling into place for a truly circular battery economy. But it leaves us with one final, absolutely critical question. Can the world actually build these complex, capital-intensive chemical plants fast enough to handle the battery tsunami that's already on its way?